So how can we speed up a chemical reaction? Well, you need to decrease the height of the activation energy barrier somehow. So you need some way to develop a transition state or activated complex that requires less energy. Okay. And there are two major ways that you can do that. So we're going to discuss in this lecture two ways that you can speed up a chemical reaction. The first way is by throwing in a catalyst. Okay, so catalysts are agents added to a chemical reaction that do two things. They provide a lower activation energy barrier, and they are recovered unchanged from the chemical reaction. So catalysts are species that you add to a chemical reaction that are not reactants. They facilitate the reaction by decreasing the energy of the transition state, but they do not participate in the reaction. They don't have their own bonds broken and formed on the way to becoming products in the same way that reactants do. Now, catalysts can be biological. Okay, so biological catalysts are called enzymes. And enzymes are proteins that speed up reactions, biochemical reactions. But catalysts can also be abiotic. Okay, you can have a lots of catalysts contain metals, so you can often throw in a metal, and the surface of the metal will provide a location for the reaction to occur on. So a catalyst can be totally abiological. But the thing that all catalysts have in common is that they speed up reactions by providing lower activation energy pathways. Oh, and the beauty of them also is that they become that you can reuse them because they're recovered unchanged from a reaction. Okay, they're not converted to products, so you can recover them at the end and reuse them over and over again. So let's illustrate how catalysts work by drawing reaction coordinate diagrams where we have energy on the y-axis and the reaction progress on the x-axis for each of these diagrams. And I want to draw a reaction progress diagram just for any old exothermic reaction where we have our activation energy barrier. So the energy of the products is a little bit less than the energy of the reactants, and that wasn't very pretty. So I'm really not good at drawing freehand with the stylus here, as you can see. So as you recall from the previous lecture, if we look at the kind of the difference in energy between the energy of the reactants and the energy of the products, that gives me the delta H of the reaction. Now, the difference in energy between the energy of the reactants and this peak here, this maximum here, gives me the activation energy. And again, the activation energy is the barrier that needs to be surmounted in order for the reaction to happen. So now, if I'm drawing the same reaction, so this reaction that I just drew is for the uncatalyzed reaction, let's say, the reaction without a catalyst. Now let's draw what the diagram would look like for the catalyzed version of the same reaction. So the energy of the reactants doesn't change, and the energy of the products doesn't change. What changes is the height of that activation energy barrier. So what a catalyst does is it shrinks the height of that barrier so that there is less of an obstacle to overcome to make the reaction happen. You'll notice from this diagram that the delta H of the reaction is the same as it is in the uncatalyzed reaction, okay? Because the energy of the products and the energy of the reactants are still the same, and the delta H of the reaction only depends on final state minus initial state. So a catalyst works by lowering the activation energy barrier, by creating a transition state that is a lower energy version of the transition state. So two things to note about this. In these two reactions, the uncatalyzed and the catalyzed, first of all, the delta H of the reaction remains the same for both of them. Delta H is a thermodynamic state function. It is independent of pathway. Okay, so thermodynamics are not affected by catalysts. However, the rate of the reaction is going to increase when you add a catalyst because the catalyst provides a lower energy pathway for the reaction to happen by creating a transition state that's not as unstable. Okay, by creating a more stable transition state, it lowers the activation energy barrier. That's how a catalyst works. Okay, so we can look at this also in terms of our energy distribution diagram. So you may recall this diagram from the previous lecture where we're plotting the number of molecules as a function of energy, and only molecules with activation energy with energy greater than or equal to the activation energy will be able to form products in any given chemical reaction. Okay, so you may remember this diagram from this distribution diagram from the previous lecture. So if this one that I just drew, let's just say that this one is the catalyzed reaction. This activation energy pertains to the catalyzed reaction. The uncatalyzed reaction would have basically a higher activation energy. So let me get a different color here. Get this dramatic color here. And I'm going to say that this activation energy here would pertain to the uncatalyzed. Okay, so I don't know if you can see that. Let me clean this up a little bit to make it more easy to read. So this is the activation energy of the catalyzed reaction. Okay, so what this means is that for the catalyzed reaction, the activation energy is less than for the uncatalyzed reaction. Okay, and more molecules are going to be able to do the reaction in the catalyzed version because you have the distribution basically means that more of the molecules will meet the requirement, will be able to surmount that barrier. Okay. Another way that I can draw this to make it more obvious is to color code it. So all of the molecules represented by the red hatching are going to be able to react in the catalyzed reaction, whereas only the molecules above this barrier here are going to be able to react in the uncatalyzed reaction. So this diagram simply shows that the catalyzed reaction will have more molecules, a higher number of molecules with sufficient energy to react. Okay, so that's catalysts. Now, another way to speed up a reaction involves playing with the temperature. So chemical reactions are highly temperature dependent when it comes to how fast they go. In fact, almost all reactions are going to speed up as temperature increases. And this is because when temperature goes up, molecules are moving faster. They're colliding into each other more frequently and with more force. And that tends to make reactions happen faster. So the general rule of thumb for chemists is that reaction rates double with every 10-degree increase on the Celsius scale or Kelvin scale, same size of degree. So with every increase of 10 degrees, the reaction rate approximately doubles. So that's a pretty massive temperature dependence. That's not always true, but it's a rule of thumb. So this is kind of best explained, again, by looking at the energy distributions as we did for the catalysts. So once again, we're looking at the number of molecules and the energy that each of those molecules has. So let's say I'm looking at a reaction with a certain activation energy, as denoted by the red activation energy here, okay? So let's say that this is temperature number 1. Now, if I jack up the temperature to a higher temperature, the distribution of the energies of the molecules is going to change. Now, more molecules are going to have higher energies. So this is at temperature, the blue line is temperature number 2. And this is where temperature 2 is higher than temperature 1. Okay, so when I have a higher temperature, I have more molecules with higher energy. So that means quite simply that at the higher temperature, so at T2, there are going to be more molecules, more reactant molecules that exceed the activation energy. You can see that from the distribution diagrams. And if you exceed the activation energy, that's all you need to surmount the barrier on the way from reactants to products that exceed activation energy. And thus, the rate of the reaction increases. Mathematically, what this means is that you have a larger rate constant K. All right, so in the next lecture, we will take these concepts and develop an equation to make it quantitative so we can see the relationship of the rate constant and temperature.